The most important and underrated parts of creating a drone is making sure you have the most lift for the least power input. And to do that, you need to take into account with the design of the blade just how lift acts on rotating airfoil. There are a lot of theories for how things fly, but the simplest is the Bernoulli principle, which essentially states that air moving in an area of high pressure will always want to go to an area of low pressure. Think of it like a giant paintball gun. Air moving over the bottom of the wing is the CO2 canister, and air moving onto the top of the wing acts as the air just outside of the muzzle, creating a force from the area of high pressure to the area of low pressure, also known as lift. Because of that, the two really important factors of lift are airfoil area and speed, since both allow you to get more air underneath the wing and create a higher force upward. It's different in a drone blade, since the speed highly depends on the radius, which means area at the tip of the wing is going to get a lot more lift than area towards the center of the wing. Which also means we're going to want to have a tad a lot more area at the tip of the wing, as most drone blades are designed. Now, what I've done is that I've gone into Onshape and created a design for what an efficient blade should be, and created an additional geometry as a circle to define the rotation zone. I've created a 3-blade design because that gives us around 50% more lift than a standard 2-blade design for a racing drone would be, plus any extra lift gain from the increased area at the tip and the decreased area at the end. To run the simulation, we're also going to need a mesh, which is essentially just a series of thousands of partial differential equations called cells mapped upon each other, with more specific refinements for where to include more cells and where to exclude them. So in this case, we want more cells around the area which the air is going to be fluctuating, like the area around the blade, but we're having a lot less cells in areas where air is slightly less affected. After running our test, you can see that the pressure force at Y is about 4 newtons, which might seem like a little, but keep in mind that this is only one of the 4 motors, and we're not running it at the maximum RPM of most racing motors today. We only ran it at about 1,200 RPM, which is way below standards.